In today's tutorial we will have a look at the radicalic bromination and especially at the selectivity for the bromination, radicalic bromination of Norbornane. Here we have the structure of Norbornane. It's a bicyclic hydrocarbon, and since we know the rule that in radical reaction tertiary CH bonds are by far the most reactive, we would anticipate that the radical bromination will take place at those bridgehead carbons. Well, this would be the anticipated product. However, if we have a look in SciFinder, what are the real results of this type of reactions, we will find that we would achieve less than 3% of the anticipated product. The main product is that of a bromination at those CH2 groups here, the 4 CH2 groups there. 97% of a mixture of the bromide with the exo and the endo position we would obtain. It seems to be that almost nothing of a bromination here at that CH2 group is formed. So how could we explain that the old rule, tertiary CH groups are by far the most reactive for radicalic reaction, does not work at a system like that? Therefore, let us have a look at a typical example where this rule works, tertiary butane. This CH group, a tertiary CH group, is by far more reactive. 6,300 times more reactive than those primary CH3 groups. Well, there are two reasons. One is release of steric strain, stabilization, two reasons for the stabilization of the intermediary radical. So if we abstract a hydrogen atom here, then a radical center will remain here, and well, there is some release of steric strain because with the change in hybridization from sp3 hybridized center to an sp2 hybridized center, those CH3 groups will increase their distance. This is then a planar system with a p orbital in the center and a radical electron here. So the second reason for stabilization is the so-called hyperconjugation. Well, imagine we have the radical center here, and we can now visualize it by mesomeric structures. Let's assume that we have partially a double bond character here and then a radical hydrogen there. This is not real intermediate, it's just a mesomeric structure, some kind of visualization. Well, here I think this model is far better than those mesomeric structure. Oh, we have a p orbital here with a radical center, and then having a CH bond here in the alpha position, which will consist of an sp3 orbital and overlapping with that hydrogen here. Well, if this CH bond and this p orbital are oriented in line, we would say they are periplanar, then overlap can take place here, and overlap between orbitals with electrons in there. This is a bond formation. This symbolizes that we have a little bit of double bond character here, strengthening this bond but weakening that bond. And this can be visualized by those mesomeric structures. So, both factors, release of steric strain and hyperconjugation, can't take part here at the Norbornane system for the bridgehead position. If we have a radical center here, no release of steric strain, since that system is rather rigid and no planarization can take place here. No change or almost no change from sp3 to sp2 hybridization, and as we see, the p orbital is here now it's not a p orbital, it's still, as I said, an sp3 hybridized center. The orbital with a radical electron is still here in front, and this is, well, almost perpendicular to those CH bonds there, and therefore no overlap takes place, no hyperconjugation. Well, and I think this is a good explanation for the fact that we have almost no bromination at the bridgehead position in the case of Norbornane. Thanks for listening.